about
there.
now?
Yep.
All right. One more time. I will be talking about type stability in Julia, a program property that relates to performance. And Julia is big on performance. Its domain is scientific computing primarily. So let's look at one little benchmark that shows how performance can be affected by the set property. So the benchmark is well known, called PySum. It's a nested loop that computes the sum variable, and baseline runs in 5 milliseconds. So now I will modify the program a little bit to insert a call for identity function. And the identity ID1, it's called, it's a little tricky. It's not just that it returns its input like a normal identity, but it returns it conditionally on the never variable. So never is just a global variable initialized as false. So we'll always take the else branch. It doesn't matter really, we return the same thing on every branch. And surprisingly, the optimizer is fine with that. It still runs in 5 milliseconds. And here I will make another modification that actually harms performance. So we use the same points in the program to insert another identity function that's called ID2. And ID2 never returns a string with this nice red cross, and it always returns the input x. So it behaves like a reasonable identity function. But suddenly optimizer hits a snag here, so the program runs more than twice as bad. So what happens here when Julia programmer hits a performance regression? They usually reach to the utility called code-worn type. So code-worn type prints a low-level representation of the code. So in this case, the PySum2 function. And that low-level representation largely resembles SSA. So it's every statement is an assignment to some virtual register or a local variable. And every assignment has a type. So those virtual registers Julia calls slots. And every slot has a typing. So here the blue types are kind of good. And the whole printout have only one point where something goes awry. So as we expect, it's a call to ID2, at which point the compiler is not sure whether the ID2 returns int or string. So it's one of the two. So this lower level representation, it's called method instance for the PySum. And we can go deeper and inspect a method instance for ID2, which is sort of the culprit of our problem. So it's much shorter. It shows that ID2 returns either X or the string. But the body of and that means the return type of this method instance, when ID2 is compiled for the input of type int64, the return type is again unclear. It's either int or string. So type stability is tries to capture exactly this property that the optimizer can predict the precise return type on every method call in your program. And ID2 in our example is not type stable, so given an int, it returns either int or string. And for float, it will be float or string, and so on. And PySum2 is in fact type stable, so it always returns a type of float, but it suffers in performance because of instability of ID2. So there is this conversation between sort of APIs that care about performance and APIs that may jeopardize your performance when you call them if they are unstable. So my thesis statement is that type stability is a widely used program property that can be used by a compiler to generate correct and efficient code, and can be approximated by automated techniques. To support this statement, I solved 3 research challenges in this work. I first assess the large corpus of Julia code to see how much code actually exercise the property. So, it can be trivial, or it can be, it can be everywhere, it can be nowhere, or it can be in between. So we wanted to look at how often we see type stable code in practice, and whether any code patterns associated with this property. That's the first challenge. The second one, I establish a formal correspondence between that property and code optimizations, and prove optimizations correct. And thirdly, I don't want programmers to reason on the level of IR, and rather I want them to reason on the source level. And for that, I try to approximate type stability statically, and sort of give the programmer ability to talk to the tooling and analyze the source code instead of the internal representation. The papers published during the course of this work is as follows. First is the UPSLA paper that forms the basis for the first two research challenges, although in the dissertation they are expanded, and there are the full proofs are provided only in the dissertation. There are some additional graphs and stuff like that. The second paper forms a basis for the third challenge, the approximation problem. It discusses Julia's subtyping relation, and subtyping, as we will see, will be a great tool that helps us to solve the task of dealing with type stability on the source level. And lastly, the overall approach for the third challenge was recently accepted for the MIL workshop. It will be presented in the end of October. And we are working on a full paper submission, actually, for this piece of work, too. So let's get to the first research challenge, which has to do with analysis of the Julia packages, the packages from the Julia ecosystem. So our approach here is that we pick popular Julia packages. We instrument the Julia implementation in a way that running a test suite for a package, and most of the packages have test suites in Julia ecosystem. So we instrument the virtual machine in a way that after running a test suite, we can inspect the internals of the virtual machine to define which method instances were compiled during the course of the test suite. And we analyze the type stability itself and some related properties. So roughly the quantitative part of this analysis is as follows. We have the corpus of 1K packages, which tests indicate largely type stable code. So it's 3/4 or 74 and 80 median % of the instances are stable. And we also, so these numbers by itself, they answer the question in general. We zoom a little bit on the top 10 packages and see that there is not much variation around the median here. The interesting parts are the Genie package that has 93% of stable method instances. And it's a web server that very clearly on its README page says that they care about performance, and even some commits in their Git history claim that they fix type stability regressions at some point. So that's one sort of extreme point. And the other extreme point is the KeyNet package that only robs the CUDA API, which is as a C sort of implementation C API. And the Julia part of the package is actually not very concerned about the performance. So this 16% is surprising until you know the domain of this package. Once you know it, it's not at all. We also did a little bit of qualitative analysis that helps us to sort of figure what type stable code looks in general, or most likely. So when you see that function and you analyze it via some automated technique, you most likely see one of those several patterns. So first is this type constant function that always return the input of the same time. So here is even as generic. You see it can accept any type, value of any type, but it will always return a bool. So that's pretty common. A little bit more general case is generic transformations. So functions that, for example, manipulate containers. So in this case, we union two multisets. It's also, it will come out as stable because it always returns a multiset of something. So it may be multisets. So in the actual test cases, it may be multiset of int or float. It doesn't matter that the type itself is concrete, and so that's why it's also a pattern of stability. And the last point here is that some generic functions actually inspect the parameters or the values of the type parameter, and in that case, it really depends on what you call it with. So if you have a vector of integers, then the return type, the first element, will be an int, and that's type stable. But if you call it with a vector of any, for example, so vector of some, pointers that hold something which is possible in Julia, in that case it will not be stable. So these are the main patterns that we saw. And after we did a qualitative and quantitative analysis, we can turn to actually pinpointing what we mean when we say type stable. So before, we mostly used the Julia's manual definition, but it's not enough to solve the second challenge, which is to formally connect the property and code optimizations. So in order to do that, I need to be a little more precise about the types in Julia. So roughly the whole vast family of Julia types is divided into pins. So first is concrete types, which runtime values will only have concrete types attached to them. And the two major groups of such types are the primitive types like bools and ints. Generally, whatever LLVM backend understands can be primitive, and even more than that, but Julia actually it allows, but discourages you to define your own primitive types. And then the common case for the concrete types is user-defined structs. So they are aggregates of other values. User-defined, so structs are always concrete, but they may be declared subtypes of some abstract types. So in this case, the add syntax node, for example, can be a subtype of, or declared to be a subtype of the expr, generic expr type. And so abstract types can also be declared, so for expr, for example. But there is also a number of important common cases for abstract type that you'll see in Julia programs. For example, union, we already see it, so it's either or kind of situation. And those are non-discriminated unions, so there is no tag that you can check that says it's either or. But that just means that compiler does not know what pops up at runtime. It will be either int or string. And any means, as I mentioned before, basically any Julia type can pop up at the runtime. Abstract types are best for optimizer, obviously, so that's why we want to avoid them and want to be as concrete as possible. So the other thing that we need to analyze when we start pinpointing the performance implications of type stability is what is the main cost of using any Julia code whatsoever. So any simple, even the simplest operation that you can imagine in Julia, by default, without any optimization, will go through multiple dispatch. So for example, when you add two numbers, so two integers in this example, you'll have to go through again, by default, without optimization, through the whole method table, so all versions of plus defined in the current environment. And even the base environment, the standard library, defines more than 200 methods for plus. So it's a rather sort of slow mechanism. It makes Julia programs very flexible, so you can always add your versions of plus. But it has its real performance cost. And not only the mechanism is slow, but also it prevents. So if you don't know what you will dispatch to statically, then you will not be able to predict the return type, and then you will not be able to optimize the program further. So for example, the next best optimization would be unboxing, so you won't be able to unbox the result, and so on and so forth. So that's one of the key one of the key price that you pay in terms of performance. So that's something we should bear in mind when we build the formal model. So our formal model called Joules, it's modeled after that low-level IR that we saw before. So it's a list of assignments, and with at a very simple right-hand side, so to speak. So the Joules need to reason about abstract versus concrete types. We don't need really in Joules to go into details of user-defined types or unions or anything. We really just need this distinction between abstract and concrete, and that's what we do in the dissertation. And the second point is that if we want to reason about optimizations, we need to be able to say, how do we do better than just doing multiple dispatch on every call? So that's why there is a special syntactic form for so-called direct calls. So in Joules syntax, you can have what you usually have in Julia sorts, which is the normal syntactic form for a method call, which by default goes through the dispatch. Or in Joules, it always goes through the dispatch. And the second form is called direct call. So you see this bang, and the concrete input types for this call so this means we know statically what types of values are held in these registers N and M. And in this case, we know exactly which instance of G will be picked from the method table. So Joules has two semantics. First, dynamic dispatch baseline semantics, where we don't run the optimizations at all. So every call, every function call is actually a dispatched call. And the second semantics is the interesting one, which is the JIT compiler. And we proved that those two semantics coincide. So in math notation, this says that we have the dynamic dispatch semantics, which is right arrow D, and we have the JIT semantics, which is right arrow JIT, and they will run basically to the same results, which results are stored in the environment E. So you see the E here is the same as here. And so how does the initial program look is that the environment is empty, and it has a bunch of statements to execute, and it runs to the empty set of statements and the environment. So the result will be the same, but you will notice this little prime on the method table. So the second component of the configuration is the method table. The dispatch semantics, the baseline one, does not modify method table. The JIT semantics, it does. So what it does is it specializes. So it's a type specialized in JIT compiler. So it adds specializations to the method table. And let's see what it does. So every specialization is meant to be an optimized version of something that was already in the method table before. So how do those optimized versions of methods look like? So imagine we have that f function in the method table. And we know that f is called with the concrete types T0 and T1. That's important. We only do any optimizations once we get concrete input types. The first step that we do here is we call the type inference engine. And in the paper, it's model, or in the dissertation, it's modeled as an oracle. We don't really define an algorithm for that. We just define a set of formal requirements for the type inference engine, and that's I think interesting in its own. That not any type inference algorithm will work, but just the sane one, which Julia's one is. And the type inference engine will return the typings of those slots, the %2, 3, and 4. And based on this information, we do the optimization. So what do we do here is we look at every function call. So first function call is G, for example. We see that G is called with %0 and %1. So that means, and %0 and %1 has known, statically known concrete type, or compile time known. So we do all of it at runtime because of the JIT, of course. But at the time when we call the JIT, we know the concrete types for inputs of the G call. So we can replace the dynamically dispatched call with the direct call. So that's a success. And then we go over all other slots and look at the other method calls. In this case, H has a call with 2 parameters, but unfortunately, we won't be able to devirtualize H call here because the %2 slot has the any type, so which is an abstract type, so the optimizer won't do anything here. So as a result of defining these two semantics, we were able to establish the correspondence between the type stability property and optimizations. But with a little help of another notion that we call type groundedness. And type groundedness is sort of a limit or an ultimate state of a method where you can get the best optimizations possible. So type stable methods only, we know about them that they return a value of concrete type. For type grounded calls, we know that all the slots, so slot %1, %2, and so on, are inferred to be of concrete types. So when you get to this state, you are able to get what we call full devirtualization. So basically, all dispatched calls are devirtualized by our JIT. And the second theorem that connects type groundedness and type stability says that if you have type grounded method, or you want to strive to be type grounded, you need to call a type stable method. So one non-type stable callee for you, and then some optimizations may fail. So that concludes the second challenge, which connects the type stability property and the optimizations. And the third challenge here is that we want to reason about type stability on the source level rather than on the level of IRs. So let's see. So that's the problem. You see the PySum function had 4 or 3, something like that, not many lines of code, excluding the ends. And then when you call code-warn type on it, you have a very long string of assignment statements. So that's much harder to analyze, and it's not clear at all how one relates to another, actually. So how do we go about figuring type stability without, resorting to the low-level representation? We first try to, identify the concreteness of the output based on the information that the input is concrete. So in some radically simple case, it can work because, the concreteness bit can be carried over. But in mildly more interesting case, as I said before, multiple dispatch is everywhere in Julia. So when we call that plus, there is 200 methods that can be called, and we don't really know what the return type would be and what the concreteness of that type would be. So in order to reason about the concreteness of return value, you need to deal with the dispatch somehow, and in order to deal with the dispatch, you need to have some idea about the types of the method calls again. So it almost feels like we need some kind of type inference going on to define the concreteness of the output. But Julia already has type inference. Remember, I just showed you that in our model, we routinely call type inference engine that Julia has. We just need to supply concrete types to it. And that's the sort of the real challenge here. So the overall approach for inferring type stability in my work is that you get the method object, you get its input type, and then crucially, you try to enumerate all or as much as possible concrete subtypes of that input type. They will represent the actual inputs at runtime. And then for every concrete type, you can run Julia's type inference and check the result for concreteness. And then you loop back, trying to again exhaust all the possibilities. So in a code that would look like something like that. So you get the method with the which macro of Julia. So it's a runtime object. You can inspect it. You can extract the signature from the method. You can define a concrete input type. So here you see the type annotation for the length method is array. So it's some array. So it's an abstract type. And we can, toss some concrete type at the type inferencer. So let's say I want to check the stability against array of floats and one dimension. We run the type inferencer, and it's able to determine the return type as int, and int is a concrete type. So as I said, the main challenge and so the overall approach is reasonably straightforward. The actual challenge here is how do we get those concrete subtypes? First idea is that we have one built-in utility that does something similar to what we want. It given a some type name, it will, so for example number, it will list you all the declared direct subtypes. So complex and real are declared with type abstract complex subtype number. So those are direct subtypes of numbers of the number type. And so there are just two direct subtypes, but there is much more subtypes if you try to recursively call subtypes on complex and real. And we need to sort of do this sort of transitive closure against the input type. So we will have to call this many times to get to actual concrete type. So for example, integer will be somewhere in the real bucket, I believe, but you will have to call subtype several times. So the issue is that the names that we call subtypes, again, the built-in utility, is only a tiny piece of the Julia type language. So there is much more than that. So there are union types, there are tuple types, there is something called existential types. So we'll see how they behave in a moment. But the array type we saw before is an example of existential. And there is a little more. So these are the main sort of interesting points in this challenge, is that subtypes don't know anything about subtypes of union, tuples, or existentials indeed. So my solution would be to extend the subtypes in a way that it can deal with all those type constructors. So that's what I do in my dissertation. So there is, as I said, a bunch of type constructors for union. It's more or less trivial. The direct subtypes of this union type is number and char. The direct subtypes of tuple types will need to actually call the subtypes, the built-in utility for number, because it's abstract. It doesn't need to touch char because char is already concrete. So it will call subtypes on the number. We know that subtypes on number returns complex and real. So, and then we will sort of fill in this spot with the results. So the direct subtypes will be as follows. The more interesting case is the existential again. So the existential type is, so direct subtypes of it should be like so. So you have pointer type, that's parameterized with one type, and the possible instantiations of pointer type would be, pointer of all floats, all ints, and so on. So that's a little bit, it breaks the pattern where you can call the subtypes function. It's the built-in subtypes function, or direct subtypes recursively right away. So in order to generate all this long string of possible instantiations, you can you have to be able to collect all subtypes of number instead of just direct subtypes of number. But that's fine, because we do need all subtypes eventually, because our final goal, remember, to enumerate all concrete subtypes. And in order to get to concrete subtypes, we may need to go all the way down through the subtype lattice. And that's what we have to implement anyway. But that's, here, that's the result for the bounded existential. So this means the T parameter has the upper bound of number. That's why we see the number types here. So what do we do with what I call unbounded existential? So that's of course, every existential in Julia is bounded by, but the bound may be any, which means we don't know anything whatsoever about the upper bound. So that's what I call unbounded existentials. And for the array type, it's actually a shorthand. So we saw the just array. What it means, in fact, is array T and N, where T where N, and both of those variables has the widest possible ranges. So from bottom to top, which is the any type. So it means we can instantiate the parameter however we like. And here, those are the examples how we can instantiate the parameter. But of course, there are infinitely many of those instantiations. So this is the real problem here. When you see any, you have to deal with infinite number of possibilities, in fact, due to how Julia's type language is set up. So what do we do with any? So there is a couple of ideas that we apply in this work. First, it's we don't try to enumerate any at all. So when you see a hard problem, just don't try to solve it at all, right? That's one of the approaches I try to apply. So for example, in the example of length, so length is what I called in the first research challenge type constant function. So length always returns int. So we don't really need to work all that hard to figure that the return type is int, and neither should the type inferencer. So we just need a type that will kick in the type inferencer, and the natural choice here is to take the type that comes from the method signature, right? So length has the array in the signature, so we call the inferencer with the array, and we get the desired result. So we don't really need to even go into all the trouble of enumerating subtypes of this existential. The second idea is, of course, not all type stable functions are type constant. So sometimes we do want to still enumerate some concrete types. We won't be able to enumerate everything. So the problem we hit is that we start from the top, or from some abstract type, and we try really hard to get down to those bottom, the leaf types, which are the concrete types and subtypes of the input. But so we fail on this way because we can't find a finite path there. Or we want to actually find all the finite paths for all the paths there, and some of them are infinite, in fact. So the idea would be, the natural idea would be start from bottom and just pick some concrete types that satisfy the input type. So, and as we say, any is the major sort of pain point here. So for any, it's really simple to satisfy what we want, because any concrete type would work. So the question then turns into what concrete types we want to sample. So we won't be able to enumerate all of them, but we'll be sampling for some of them. So where do we get some of those concrete types? So we again apply the harness that we used in the first part of this work, and we run the test suites of the popular packages, and we record what types you are used to instantiate the methods during the tests. So, and we create this little database sort of thing of Julia types that we can leverage to enumerate all the possible input types. So the first, I should have said, the first idea, the concrete type inference with abstract types, doesn't lose any precision, whereas the sampling approach does. So here I compare. So the first idea is no-brainer. You just put it there and it will work. It will not harm the result, the existing engine in any way. It will make it faster, if anything. But for sampling, it's subtle how the results change their meaning a bit. So here is the comparison for every of those 10 packages. We have 2 bars. Left is no sampling, and so we just say we can't enumerate the concrete types in finite time, and we say timeout. So that's the gray area. And the right bar of for every package is the approach with sampling. So the results become they become better. Obviously, we can always handle more cases. That makes sense. The meaning of the bars change a bit. Actually, only the meaning of the stable portion, so the blue portion of the bar changes. So the red portion of the bar is unstable, meaning we found the counterexample either by enumerating as before, as we did in the base approach, or we find the counterexample by sampling from our database. So that's still good. This stable bar is a bit different, as I said. It means that, so in this case, stable means that we may have hit any during the enumeration, and we sampled and we didn't find any counterexample. That means that we decide that it's the method is stable. And I should have said sampling is kind of nicely. So if the idea of type inference with abstract type, the first idea to handle any, maps nicely on the type constant functions, the second idea with sampling maps nicely on the generic functions. So if you remember that example with union of multisets, if you sample, multiset of int and multiset of float, and all of them always return a concrete type of a multiset, then it's it's okay. It's most likely it is type stable. But yeah, that's a little subtle difference between those blue bars. The results are so not surprisingly different from Genie, which was the very, very type stable package. The results are a bit different from KNet, or quite a bit different, because the baseline is very low, as we saw in the dynamic approach, but this sort of sampled but couldn't find the counterexample kind of stable, this blue bar here, it grows to nearly 50%, which is a lot for KNet. Remember, the dynamic analysis got only to 16% of type stable instances. So I already started comparing the approaches of tracing and approximation. So tracing is something I did in the first part with the running tests and inspecting the internals of the virtual machine. So the good news, so to speak, is that the results of approximations are not much different from the tracing part. So this can mean various things. They are not directly comparable because we actually compare different sets of methods. The tests explore only some methods in the package. The approximation explores all available functions in the package. But still, I think it's a good news, and it's only, these numbers are only for the top 10 packages. So if you imagine some lesser known package which may not even have the tests or the good test suite, then you can still run the approximation because it doesn't rely on test suite at all, and you still get some numbers which would probably reflect the reality in some way, which you can't really rely on if you don't have a test suite at all, or you have a minor test suite. So that concludes the evaluation part of this approximation work, and also concludes the thesis. I think I ran about the right time, So let me just stop here and invite in any questions if you have anything. And let me stop the Zoom recording.
Okay, thank you, Artem.